Welcome to today's Explainer. Today, we're going to absolutely master flight and fuel planning, taking you from a student pilot to a command-ready captain for your DGCA CPL air navigation exams. If you've ever wondered how real airline pilots make those split-second life-or-death decisions about whether to turn back or push forward when things go wrong, well, you're in exactly the right place.
Here's our flight plan for this session. First, we'll decode the core concepts. Second, we'll tackle the exact mathematical formulas. Third, we'll look at some DGCA exam trick questions. And finally, we'll wrap up with a rapid-fire revision to lock it all in.
Section 1. Concept Explained. The high-stakes reality.
Okay, let's put you right in the captain's seat. Imagine you're flying a twin-engine aircraft 300 miles over the open ocean on your way from Chennai to Port Blair. Suddenly, boom, you lose an engine. The clock is ticking, your speed is dropping, and your fuel consumption profile just changed entirely. So what do? Do you turn back to Chennai or do you push forward to your destination? This is the exact dilemma that proper flight planning solves before your wheels even leave the ground.
But before we can even dispatch that flight, we have to talk about fuel. Under DGCA CAR Section 8, you can't just fill up the tanks and go. Your total fuel on board is legally broken down into strict categories. Taxi fuel to get you to the runway, trick fuel to get to your destination, a mandatory 5% contingency for unforeseen stuff like weather deviations, your alternate fuel, and finally, a non-negotiable 30-minute final reserve. That final reserve, that is your absolute bottom-line survival fuel. You literally must land with it completely intact.
To answer our ocean emergency question, we use what's called the critical point, or CP. Sometimes you'll hear it called the point of equal time, or POT. This is the precise geographical spot on your route where the flight time to continue to your destination is exactly equal to the flight time to turn around and go back. And here's the kicker. It is completely independent of your fuel. It's a pure time problem, driven strictly by your outbound and homebound ground speeds. Think of it like a giant invisible boundary in the sky. If your engine fails before you cross that critical point, your fastest route to safety is turning back to your departure airport. But if the emergency hits after you cross the CP, you're committed. Pushing forward is now officially your fastest option. Like I said, it is all about time.
All right, but what about your fuel limits? That brings us to the point of no return, or PNR. Unlike the critical point, your point of no return is a hard, physical boundary dictated entirely by the fuel in your tanks. It's the absolute furthest point you can fly away from base and still have exactly enough fuel to turn around and land back at your departure airport with all of those mandatory regulatory reserves totally intact. It relies on your safe endurance, which is just your total usable fuel minus those legal reserves we just talked about.
Section 2. The numbers and formulas. Okay, grab your notepads, because we're transitioning from theory into the heavy calculation mode you're going to face on the exam.
Before we even touch a formula, you've got to instantly recognize these standard navigation variables. Capital D stands for your total track distance. O is your outbound ground speed, how fast you're moving away from base. H is your homebound ground speed, how fast you'd be moving if you turned around. And E stands for safe endurance, the time you can fly before eating into your legal reserve fuel.
Here is your golden formula for the distance to the critical point, which we'll call x. The distance to your CP is calculated by multiplying your total distance d by your homebound speed h. Then you divide that result by the sum of your outbound and homebound ground speeds. Write this down and memorize it. D times h divided by O plus h.
Let's run our Chennai to Port Blair scenario through a real worked example. Say the total distance is 720 nautical miles. Your planned true airspeed is 240 knots, and you're fighting a 40-knot headwind on the way out. Step 1, figure out the ground speeds. Outbound, 240 minus 40 gives us an O of 200 knots. If we turn back, that headwind becomes a massive tailwind, so our homebound speed H is 240 plus 40, which is 280 knots. Step 2, plug it all into our formula. 720 times 280 divided by the sum of 200 plus 280. That's 201,600 divided by 480. Do the math, and step 3 reveals our critical point is exactly 420 nautical miles from Chennai.
Now, to find the time to your point of no return, the formula is actually remarkably similar, but we swap total distance for safe endurance. You calculate the time t by multiplying your safe endurance e by your homebound speed h, and once again dividing by the sum of your outbound and homebound ground speeds. So e times h over O plus h.
Here's another heavy calculation you'll definitely face. Converting fuel from mass to volume. Fuel density changes with temperature, so we use specific gravity, or SG. Always remember this exact workflow for the exam. Step 1, convert your given mass into kilograms. Step 2, divide those kilograms by the specific gravity to get your volume in liters. Step 3, if the question asks for US gallons, you just divide those liters by 3.785. Sounds pretty simple, right? Well, watch out.
Because here is a massive trap where students constantly fail in the exam hall. They'll calculate everything perfectly, but at the very end, they multiply the mass by the specific gravity instead of dividing by it. If you do that, you catastrophically underestimate the physical volume of fuel you need. In the real world, that mistake could easily lead to fuel starvation mid-flight.
So here is the crucial rule of thumb. Since jet fuel has a specific gravity of around 0.84, it is less dense than water. This means your calculated volume in liters absolutely must be a numerically larger number than your mass in kilograms. If you've got 1,656 kilos of fuel, your volume should be over 1,900 liters. If your volume number comes out smaller than your mass number, you multiplied when you should have divided. Don't let them catch you on that.
Let's move into Section 3, DGCA Exam Focus. Let's see how they use these concepts to build the exact types of trick questions you'll face on test day.
You are absolutely going to see a conceptual question like this. They'll ask, in the presence of a constant outbound headwind, how does the geographical position of the critical point shift? They love testing if you understand the physics without actually letting you touch your calculator.
The correct answer here is that an outbound headwind moves the critical point closer to the destination. Think about it. If you have a headwind on the way out, you're going to have a tailwind on the way back. Your return ground speed is now so much faster, meaning you can afford to fly much further out away from base before the times become equal. Thus, the CP shifts toward the destination.
Here's another classic trick question pitting legal airline fuel policy against usable en route fuel. When calculating safe endurance to find your point of no return, which fuel components must be subtracted from your total fuel on board?
The right answer requires you to subtract taxi fuel, your fixed 30-minute reserve, and your alternate fuel from your total fuel on board. Safe endurance only accounts for the fuel you can actually burn while still guaranteeing a completely legal, safe landing back at your departure airport if you turn around. You absolutely cannot use your alternate or fixed reserve fuel to push your PNR further out. That's a huge violation.
Section 4. Quick recall revision. Time for our 60-second summary to lock these facts into your short-term memory before you walk into that exam hall.
Remember these key points. Critical point, it's a time-based decision boundary. Point of no return, this is your hard, fuel-limited boundary. Safe endurance, always your total fuel minus your legal reserves. And for both formulas, the denominator is always outbound ground speed plus homebound ground speed.
And burn this number into your mind right now, 0.84. This is the standard specific gravity of Jet A1 fuel. Remember, you must always divide your kilograms by 0.84 to get your correct fuel volume in liters, ensuring your volume number is always larger than your mass number.
All right, you are now fully armed to crush the flight planning section of your exam. But ask yourself this, if that engine fails at exactly your point of no return tonight, are you confident enough in your math to bet your passengers' lives on it? Theory is nothing without application. Head over to clouddeck.in to test these formulas in our simulator, and join me in the next explainer where we'll conquer aircraft's mass and balance. Stay sharp and fly